Now we'll start proving this theorem 1.66. There's an existence part and a uniqueness part. We'll start with the uniqueness part first. So this is proof of uniqueness. I'll start with the idea of the proof as usual. The idea is as follows. Since little SL2C is spanned by H, E, and F. So any C-linear representation, pi from SL2C to the endomorphisms on V is uniquely determined by pi of H, pi of E, and pi of F. But for any basis V0 through Vn of V, pi of H, pi of E, and pi of F are in turn uniquely determined by pi of H applied to Vi, pi of E applied to Vi, and the pi of F applied to Vi. For all I from 0 to n. So the key part of this proof of uniqueness is to find those basis vectors V0 through Vn that C spans V. But we are going to do more than just this. In this part of the proof, we're not just going to find any basis. We're actually going to find those bases so that those 1, 2, and 3 properties for pi and V sub i's are satisfied. So in this part of the proof, we're also going to prove this moreover part. So strictly speaking, there will be the proof of uniqueness and the moreover part. This is done through finding V0 through Vn, that C spans V, and satisfies its properties 1, 2, 3. In the statement of the theorem. Now, how are we going to find V0 through Vn? We'll find them by looking at the eigenvalues and eigenspaces of pi of H, pi of E, and pi of F. So that is the idea of the proof of uniqueness and this moreover part. Now let's prove this. To begin with, let pi from little SL2C to the endomorphisms on V be irreducible. Here, the dimension of V is n plus 1. And we are going to construct a basis for V satisfying the properties 1, 2, and 3. To this end, let's start with one vector. Let V be an eigenvector for pi of h. Eigenvectors are always non-zero. The definition of the eigenvector says pi of h is equal to some scalar lambda multiple of V. The existence is guaranteed by the algebraic closedness of this field. C is algebraic closed, so there's an eigenvalue and thus an eigenvector. The next steps are going to be very tricky. What we are going to do is that we are going to look at the following sequence of vectors. We take this V and we apply pi of e to it. And we apply pi of e again to V. We keep applying pi of e iteratively to V and get this sequence. And now we make an observation. I'll write it as a claim. We claim that they are either 0 or eigenvectors. Why is it so? This is because indeed, if you apply pi of h to pi of e applied to V, then since pi is a Lie algebra homomorphism, we have pi applied to the Lie bracket of h and e is equal to the Lie bracket of pi of h and pi of e, which is just pi of h composes pi of e minus pi of e composes pi of h. So it follows that this term will be equal to now you look at this part. Pi of h applied to V. What is this? By our construction, this is lambda times V. And what about this part? H Lie bracket E is, well, formula 2E. So this equals pi of 2E applied to V. Combining these two terms, we get lambda plus 2 scalar product with pi of e applied to v. We can pull out this lambda because its pi of e is a linear transformation. So if we repeat this procedure, what is pi of h applied to pi of e squared applied to v? This is going to be lambda plus 4 times pi of e squared applied to v. And you keep going. Pi of h applied to pi of e raised to the power k applied to v is lambda plus 2k times pi of e raised to the power k applied to v. Now since lambda plus 2, lambda plus 4 are distinct in C, here we are using the fact that C has characteristic 0. If it has, say, characteristic 2, then this argument will not work. So, for those who want to generalize this to other fields, I should remind you that we are using that the characteristic of the field C is 0, not 2. And recall in linear algebra that eigenvectors with distinct eigenvalues must be linearly independent. We have basically finished the construction part. Next, we're going to verify that v0, v1, v2 all the way through v sub n naught are the vectors we want. And this n naught is precisely equal to this n, where this dimension of the whole space is n plus 1. And the dimension of the whole space is finite. You know, this procedure has to stop at some point. You cannot produce infinite many linearly independent eigenvectors from those distinct eigenvalues. Something must go wrong in here. That will lead to the following conclusion. Since this, and this there must be a v naught in V and lambda naught in C such that number 1, v naught is not 0. And number 2, pi of h applied to v naught is lambda naught times v naught. And number 3, pi of e applied to v naught is 0. Do you see why this v naught exists? This v naught can be taken as the last pi of e raised to the power k applied to v that is non-zero. So what we are doing here is that we took V naught to be pi of e raised to power k naught applied to v from above with the next term pi of e raised to power k naught plus 1 applied to v 0. And lambda naught be lambda plus 2 times k naught. This is how we took V naught and lambda naught. Of course, this can be taken as a vector that is non-zero, because in the extreme case, you just take k naught to be 0. In that case, V naught is equal to V, which is clearly non-zero. So such a k naught has to exist. Now here comes the next tricky part. We have used H and we have used the E, but we haven't used F yet. Now here comes the F. Now define V sub I as pi of F raised to power I applied to V naught. And recall that the D bracket of H and F is negative 2F. Now we'll look at how pi of H interacts with pi of F. So pi of H composed with pi of F is this guy. And inductively, pi of H composed with pi of F raised to power I is we have done a similar thing above in here. Hence, if we apply pi of H to V sub I, we'll get first by definition pi of H applied to pi of F raised to power I applied to V naught. This is just from our definition. And now we're going to use this relation to get but what is pi of H here applied to V naught? This is number 2, right? So this is equal to, and now we pull out this scalar to the front. And we notice that this is again V sub I. This is true for all I greater or equal to 0. Now, we're going to use the same argument again. Observe that V sub I will be either 0 or an eigenvector of pi of H with eigenvalue lambda minus 2i. Now since lambda naught lambda naught minus 2, lambda naught minus 4 are distinct. V0, V1, V2 are linearly independent if non-zero. And I should emphasize this is distinct in C. C has characteristic 0, not 2. And because the dimension of the whole space is finite, it follows that there must exist some n0 such that v sub n0 plus 1, which is pi of f raised to the power n0 plus 1 applied to v0 equal to 0. And we let n0 be the smallest natural number such that v sub n0 plus 1 is 0. So in particular, v sub n0 is non-zero. This n0 is smallest such that v sub n0 plus 1 is 0. We have basically finished the construction part. Next, we're going to verify that v0, v1, v2 all the way through v sub n0 are the vectors we want. And this n0 is precisely equal to this n, where this dimension of the whole space is n plus 1.